Chase, and this is my work with Krishnamurthy and Farshad Khorrami, how to pronounce it correctly, in New York University.
Is this one? All right. Hello. I'm Griswald Brooks, and today we're going to talk to you about how we got the noun to crawl. All right. So we're going to talk about what's in the presentation today. First, we're going to do a quick review of what it is that we're trying to get done here. We're talking about the now briefly for anyone who's not familiar with the now. We're going to show you how the gait is actually formulated and little optimizations we did to actually improve the gait. So, we've had the now in our lab for a long time now. This is a video of some other work of getting into track and obstacle avoid. But we noticed that while we were doing the work, one of the obvious things that any humanoid robot can't do is go through spaces that are vertically constrained. So we figured that we could simplify the path planning problem instead of the robot having to go around certain things if you could just crawl under them. So we thought that we would design a crawling gait. These are advantageous because typically they're statically stable, and this one in particular, unlike the previous work that I'm showing you reference to here, it has a very low vertical clearance. So our gait has a clearance about 8 inches, whereas their gait, I think, is somewhere in the 10-inch range. All right, so for anyone who's not familiar with the Now robot, Now is a 25-degree freedom humanoid made by Aldebaran, just down the road there in Paris. He has a Intel Atom processor in his head. He has IMU in his chest, foot sensors, joint position sensors, IMU, sonar. One of the key points to Now is that he's laterally symmetric, so all of the joints on his left side are mirrored by the joints on his right side, something we're going to take advantage of very soon. But one of the disadvantages to Now, unlike people, the back actually lacks articulation. So it turns out that in many crawling gaits that are performed by people, they actually use their back or spine to do a twist or an arching motion in order to affect the better gait. Now can't do that, so we had to come up with something a little more cool. So the gait that we're going to talk about, we call the projected profile method. We look at Now in the sagittal plane, right? So just side view of Now. And what that allows us to do is we can take this 25-degree freedom humanoid and just parameterize it in 6 degrees of freedom. So we do this by considering a 2-phase gait, right? In the first phase, it'll show you is that the Now will be in an open chain configuration, right? So Now will be laying on his stomach, and it'll be moving his arms and feet. And then afterwards, we'll move to a closed chain configuration, where the robot has to move his center of mass to something. Put these two things together and we'll affect a crawling gait. So in the initial configuration, Now starts off laying down. When he's laying down, his chest and knees form theoretically sort of like a base that we can assume to be fixed to the ground. So that way we can position the hands and feet wherever we need to in order to affect the next part of the gait. So the next part of the gait, we actually go to a closed chain configuration where you look at the feet, you look at the elbows, and you say that that is one whole closed chain. So now we can move the center of mass from one part of the scene to the next part of the scene. Once we've come to the final position, then we can go back to the open chain configuration. Short movie of what this actually looks like. So you see that he starts in the open chain, moves to closed chain, goes back down, positions his arm and leg, moves forward. So what it looks like, if you actually take the projected profile, is this side view here, right? So from left to right, we're talking about the foot joint, the foot joint, which is the place where the foot actually makes contact with the ground, ankle, knee, hip, shoulder, and then the elbow as projected through the plane. So it turns out that if we hold theta 3 and theta 4, the knee and hip, as something to be used later, we can parameterize all 6 degrees of freedom on just the angle of the elbow, which will allow us to propel the center of mass forward. Shown here are the standard manipulator equations, right? Kinematics, not dynamics, because the whole gait is just kinematically constrained. DE is the length between the foot and the elbow. The joints are enumerated from theta 1 to alpha. L are building blocks. So briefly to solve that, you for the closed chain, you take the previous assumption where all the joint angles have the sum of alpha, with then the first two equations, and then you do a squared sum. You do a squared sum, the theta 3 drops out, you have something that's just in theta 2. These are the k's from the other equation. That allows you to come up with two solutions for theta 2 being the ankle. The thing is though, in one solution, the robot is okay, the other solution, the robot gets put through the ground. So it's pretty obvious to see which one you need and which we don't need. Once you have that, the foot joint is solved uniquely, and then the shoulder joint can be solved using the final constraint where some of the angles have to add up to the parameter alpha. So in projected profile, this is what that looks like, right? So the elbow is being swept forward linearly, and it brings the entire closed chain forward. To show a full sequence, we took now, and we wanted to actually have him crawl under something like a desk, because we have lots of desks around. So we had now actually find a fiducial marker in the environment. Once he found that, he knew his orientation with respect to the desk. He gets down on his knees, assumes the open chain configuration where he's laying on his chest, and then performs the cycle of the gates, right? So closed, open, closed, open. He does this until he gets all the way under the table. In this particular work, we just used a open loop integration. We didn't actually have any sensors for this particular thing to see when he came out from under the desk. Once he gets up from under the desk, then he gets up and then he's available to do other path lining. So having this mode actually allows obstacles that would have normally been an obstacle to a bipedal gait to not be obstacles anymore. Also, if there was an objective, like the robot having to get under something to manipulate something, this would be useful for that as well. So we left out something. We said, well, there's this theta 3 and theta 4, and we just like hold those as something else while we produce the rest of the gait. So we hold those because then we can do something interesting with those variables. So the hip and the knee we held constant, but maybe we can try to make this gait more efficient. Of course, we want our robot to, run longer, right? So that's what we do, right? We use the hip and the knee to optimize the gait to use lower torques, and we do this by using a pseudostatic formulation of the robot. So as you see, the robot moves very slowly, so the dynamics of the robot don't really kind of flesh out into the torques. It's usually just the effects of gravity. So that's what we optimize here. In order to come up with a function that maps our parameters alpha, theta 3, and theta 4, which were the elbow, knee, and hip, to the torques, we put our robot into a simulator. We ran him for 2.5 degrees plus minus 30 degrees. Took like 5 hours to get all of the table information. Put that through a linear interpolator so that we had a function, and then we used a genetic algorithm to optimize it. So we optimize with respect to the torques produced by the joint. We weighed the shoulder more heavily because the shoulder is actually the weakest of all the motors. So we weighed that more heavily, and then we added a couple of indicator functions so that the robot wouldn't try to go through the floor, which it can do, and so that it would always try to go forward instead of trying to go backwards. see here on the graph, these are trajectories for those joint angles. The blue shows the nominal trajectories where the knee and hip are held constant, and the elbow is just linearly progressed forward. The green ones are actually the optimized trajectories, and we found that there was a almost 6 times reduction in our optimization costs by doing this procedure. So, to conclude, we described the now humanoid briefly, how well it approximates a human for crawling. We described a projected profile gait, which was a dual open-closed chain formulation. Things that you can do with the free parameters that you have. In this case, we optimized the torques, but in another work, we actually used it to try to control the orientation of the back. So, as I said, one of the problems with now is that when he's looking down, he can't see forward. So if we wanted to control a laser scanner to get him to crawl under something, we want to hold the back still or be able to control the pitch and roll the description, right? So we can do that using theta 3 and theta 4. In future work, we're going to look at repositioning the arms and legs to get the robot to turn on command. And in general, any robot that can form this kind of like parallelogram structure would be able to use this methodology. So I thank you, and any questions, I'd be appreciated.
While we take questions,
No, I explained it so well that everyone's perfectly
I have a really sad question, but like the fact that you are in construction and the session for construction, is that because it's random or because actually you think that there will be application in robotic for construction?
Well, obviously, humanoid robots might be useful in construction, and so giving them an additional ability